Welcome back. We're going to do Dijkstra's OSPF algorithm. So what this thing does is it converts a graph into a tree where you're going to have roots, you're going to have a root, okay, and then you're going to have a root node, and then you're going to have destination nodes. And the destination nodes are everyone else. And the root, of course, is one node that you're going to designate. And you're going to have a path length from the root to every destination. So there's something called a distance, which is the path length, total length from the root to each destination. So we're trying to find a tree that consists of all the cheapest paths to every destination. Okay, so let me just do one here. So I'm going to do the one that's already in the notes, or it's actually posted in a separate document on the website, but that's the one I'm going to do. So we got all these nodes in here, 1, 2, 3, 4, and they have links on link weights, and these weights represent some kind of cost, right? We talked about that in the overview video of graph theory, that there's different ways to define cost. Like these numbers represent a cost of some time. Now it could be a literal dollar value cost, or it could be the latency on the line, like how fast the line is. Could be some other things. So let's choose A as the root. All right, so what we want in the end, we want to build a forwarding table. So this is used in networking. Because if you're computer A, you have all of these destinations that you want to get to. And what you're interested in this case is who is the neighbor that I need to talk to get to a particular destination. So forwarding table for node A. So let's see, definition of that is which of A's neighbors. A has two neighbors, right? B and C. So which of those neighbors gets us to each destination? And what is the total cost? And cost in this case is really it's really the same as distance. The path total length is really it's really the same thing as the cost for this particular problem. So let's start executing. So the algorithm is in the notes here, and here it is. You put nodes with the cheapest distance into the tree. You update distances and the next hop. So you need to store one more piece of information here. You have to store who is in the tree, because the distances don't go to 0 here, right? In Prim's algorithm, which we worked in another video, the distances go to 0, but the distances are different in Prim's algorithm. Right? Dijkstra's algorithm has a different definition slightly different definition of distance. But overall, it's very similar to prims. It's just the distance definition is different. And so we need this extra in-tree thing. You're solving for a slightly different problem. And then we want to know who the next hop is. As we're not storing a tree in here, we're just storing a forwarding table. Okay? Whereas in prims, we were storing an entire tree. But here, we're just storing a forwarding table. We just want to know, for A, where do I go first, right? Which one of my neighbors do I go to get to some particular destination? That's all that A cares about. I mean, if he wants to talk, A wants to talk to D, he just wants to know whether he needs to talk to B or C first. That's all he cares about. That's the way forwarding tables work. Like each computer is connected to, a certain number of other computers. Like a computer sitting on your desk might have a wire to one other computer. And in that case, the forwarding table is simple. It's just send everything to that guy. But if you have a computer that has two connections to it, you need to know which one of those connections to go to first. It's the idea of a forwarding table. So we'll execute this thing here. It's very much like prims with a different definition of distance. So we start off with A, just that's arbitrary. Okay. Then so A is in the tree, mark him as being in the tree. His next hop is not applicable because he's the root, and the distance is 0. It's not applicable really. Okay, so the candidates are B and C, and the total path length to get to B is 1, and the total path length to get to C is 2. That's what we're storing in here in the distance, is the total path length. So I could get to A, could get to B via B, and it would be 1 for the total distance. And A can also get to C via C, and the total distance would be 2. So I've updated my candidates. Their distances, but in this case, the distance is the total path length. It's not the distance to the tree. It's the distance of the total path length that is the distance from the root to the destination. And then I choose the cheapest one. So B is the cheapest one, so I put him in the tree. So this guy becomes in the tree, right? Then I update the candidate. So D becomes a candidate. He's 4 away. And E becomes a candidate with this link weight. And C might change. But let's do D and E first. So D is a candidate. He's so we're doing a forwarding table for A. So A can get to D via B. That is the next hop would be B. And the total path length via B would be 5. So what that means is that A can get to this new destination D via his neighbor B, and it would cost 5 to get there, right? So basically A knows about this new destination D, and he knows that it costs 5 to get to him, and and to get to him he has to go to B first. Right, then this E one here, the total path length is 3, and the next hop, right, is B. That is A to get to E. He would the next hop, or like the first hop, really, you could call it, is B. So let me say that again. So A can get to some final destination E via his neighbor B, and the total path is 3. What about C? C, the addition of B brought C in. Well, C was already a candidate, but let's see. It was a candidate via 2, but now the addition of B makes C a candidate with 4 total path length. 3 and 1 is 4. That's worse than 2, so we don't update that. We're only looking for new candidates or improvements in existing candidates. All right, that's it, right? Okay, so we what did we do? We just added B because he was cheapest, and that brought D and E in as candidates. And then we choose the cheapest. So the cheapest, we have 2, 5, and 3, so we choose the cheapest to put into the tree. So we add C to the tree. You don't change the distance because you need to save that for the algorithm to work, right? Briefly stated. And so we add C, and then we update candidates. So now F becomes a candidate. So F is 6 away, or has a total path length of 6 via next hop C. So A can get to, what did I just add? I added, I forgot to add this, right? I forgot to make this bold. When I added C, I forgot to update it. I forgot to make the line solid. Anyway, the addition of C brings F in as a candidate, and has a total path length of 6, and A gets to him via C, right? A gets to F via C. This next hop is just going to be B's and C's. It's just a forwarding table. A only cares about who he has to go to first. He only cares about the next hop, not the hop after that, right? As you hop around down the network on your way to your destination, hop, 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 hop. Okay, A only cares about B and C neighbors. That's what's in the table. It's a forwarding table. It's a characteristic of forwarding tables. They only have next hops in them. They have the final destination information, but how to get to those destinations, that is the next hop, is just the particular node's neighbor, because we're doing a forwarding table for node A. So the next hop link information is just going to be the neighbors. So what did we just do now? We just updated F. Let me just check to see if E got any better. Did E get better by the addition of C? Let's see. It would be 2 plus 3 would be 5. That's worse than 3. So we don't update this. The addition of C did not make it easier to get to E. And what about D? Now D is straight out, did not get affected at all. It's way the heck over here. F got added, E did not get better, and D did not get better. All right, so who's the cheapest? This guy, right? 3. So we add E to the tree. Add E to the tree like that. Mark that he's in the tree. Update the candidates. And I think something gets better here. This guy here, D, has a link weight of 1. And that would be, right now it costs 5 to get to D if he was in the tree. It would go this way, and this way would be 5, right? That's what this 5 comes from for. But now we can go 1, 2, 3, 4, right? By going this way, because this link is 1, this distance becomes 4. Still via B. Still next hop is B, but the distance got a little bit better by adding E on there. What about, did C get any better by adding E? No. It's 3 this way. Wouldn't be any better than wait, that's C's already in tree. I'm doing F. Did F get any better by the addition? No, maybe. Because right now F is 6 away, but by adding E, it'd be, yeah, it does get better. So it's 1, 2, 3. By the addition of E, F gets a little shorter path length. So this becomes it was 6, now it's 4. All right, so then you choose. So we updated the candidates. Now we choose the cheapest. We have 2 4s that are the same. And let's just say we choose the first one. So put this guy in the tree. So D goes in the tree. This link becomes solid here. And we update any candidates, see if they got any better, and nobody gets any better. And so we choose the next cheapest guy, which is put this guy in the tree right here. Okay, so this is the resulting tree. We started off with this graph and we generated this tree. The definition of distance is different than Prim's, because this algorithm overall is very similar to Prim's. It just has a different distance algorithm. And what you're solving for is it is a tree, but all you're really interested in is next hops for the root. So the tree information is sort of lost, really. I mean, we see the tree here in this representation, but in the data here, you really couldn't construct the entire tree. This is forwarding table for node A. All that A knows about is it knows that there's these different destinations that he can get to, right? A knows that he can get to destinations B, C, D, E, and F. He knows how much it costs to get to those destinations, and he knows who the first hop that he needs to go to. That is, A knows which one of his neighbors he needs to go to get to these different definitions. All right, so it's a forwarding table problem, similar in execution to Prim's, but the answer that you're looking for is different. This guy is solving for a forwarding table, whereas Prim's is solving for something different. Go look at that video. All right. I could do another, but I'm not.